Okay, welcome back, everybody. Just somebody can confirm real quick that my audio is working.
Yes, it is.
Okay, great. Thanks, Cindy. All right, so I know you've already seen a lot of technical material today. I'm going to kind of whomp you with some more. I'm going to be covering one of my favorite topics, and that is performance, performance tuning and single processor optimization. So let me go ahead and share my slides. Okay, so everybody should be seeing that in full screen now. Okay, so I'm going to be covering performance tuning and single processor optimization. If you want to follow along in GitHub, this is the URL that will take you there. So this is session 4.3a. And I just want to, oh, what happened to my slide? Oh yeah, sorry, so that was a little out of order. I've had to make a few updates specifically for today. So the exercises that we're going to be doing were originally developed for running on a full node, and they use all of the memory. And as I was benchmarking these, I'm confirming everything was working this morning, I realized that we're working on shared nodes, and we're not going to have access to all the memory. So what I had to do was reduce the problem size a little bit. So for the matrix addition example, we're going from problem size of 30,000 squared to 25,000 squared. For the fusion, loop fusion example, we're going from 30,000 down to 20,000. And for the time-based sampling, I lost track of the number of zeros, but we reduced the problem by roughly a factor of 3. Now, so that you don't have to manually change these, if you execute this command, copy-r/home xdtr107/performance, and then copy it into your home directory, that will give you access to all of the code, the scripts that we're using today. And at some point, you'll also want to get a shared node. Just type srun-shared, and that should give you pretty quick access to a shared compute node. So like I said, instead of using a whole node, I believe each of you are going to be having access to a quarter of a node, a quarter of the cores and a quarter of the memory. But if you just do a copy from my training home directory, you'll get access to all the up-to-date materials. I pasted this into the chat, and it is also available in the main room, Slack channel. So let me just back up. So, why do we care about writing efficient scalar and serial code? So, we think about it, or at least when I think about it, I see a few motivations. So I think most of us, we want to optimize our code so that we can reduce the time to solution. We'd like things to run quickly. In fact, that's why we do supercomputing. We don't want to wait months or years or tens of years for a solution. So if we can optimize the code, we'll be able to get more science done in the same amount of time, and we can shorten that cycle between job submission and results. I like to think there are a few thresholds when we can go from what previously took overnight to do, if we can now do that over the course of a day. That means we can do some calculations in the morning, look at the results in the evening, and launch new jobs. Similarly, if you can reduce the runtime from hours to a few minutes, say the amount of time it takes to do a quick walk or take a coffee break, again that will accelerate your science. Second of all, computer time, especially on high-end resources like Expanse, is limited. In fact, it's so limited that today we're using shared nodes rather than dedicated nodes. So you're going to be competing with other users for these resources. I know that some of you may already have allocations through Exceed. That was a competitive process. You or your PI had to write a proposal, competing against everybody else who wanted time in these machines. If you go to the cloud, Yeah, resources, the cloud is elastic. Um, the resources, as far as you're concerned, are almost unlimited, but you're going to be paying real money for it. And then finally, if you've been following the news lately, you realize that climate change is becoming more and more of an issue, and computing uses a lot of energy. And in this bullet, I was kind of fuzzy because I've seen different numbers. It's really hard to estimate this. But generally, there's an agreement that at least a few percent of US energy consumption is used to power computers and networking equipment. So we'd like to, we'd like to make our calculations as green as possible. I covered the updates already. So you might be thinking in terms of time to solution, won't going parallel save me? We're going to see a lot of talks this week about, well, you saw one already on high performance computing with Python. You're going to see talks on OpenMP and CUDA and MPI. So I'm going to say, first of all, most parallel applications have limited scalability. And even if your application has perfect linear scalability, there's always a more challenging problem that you want to solve. So if you can optimize that underlying serial code, you can go to higher resolutions and look at larger systems, incorporate more accurate physics, run longer. Say if you're doing molecular dynamics, you can go out into the microsecond range sometimes. You could do more replicates, bigger ensembles, better statistics. So essentially you'll be able to do more science. And of course, as I mentioned, resources are still limited, and we do want to reduce our energy footprint. So this was a report that I found last year. That this came out of LBL, Lawrence Berkeley Labs, and they were predicting just a modest growth from 2014 to 2020 in terms of how much power is used. But even so, even if this stays flat, 70 billion kilowatt hours or 73 billion kilowatt hours, that's a lot of energy, and we would like to try to keep that down. And even if we're going to keep it flat, we'd like to get more science done per watt. So before we get into some of the details, we're going to go over the guidelines for software optimization. So first of all, I think of this as the prime directive of performance tuning, and that's don't break your code. I've done this already. It's really embarrassing when you do this and you don't realize it, but make sure that you're still getting the correct results. It's very easy to get the wrong results quickly, but you need to constantly be testing your code as you're making these changes. Taking the results, making sure that they are the same or that they're the same to within, floating point rounding error. You also want to profile your code so that you know where to focus your effort, and that's going to be the first topic we get into. If it's a small application that you wrote yourself, you probably know where to start. But often software is big. The one that comes immediately to mind is CESM. It's I forget what the acronym stands for, but it's the widely used global climate code. And I believe that it is now over 1 million lines of code. So you can't just jump in there and start tuning. You don't want to obfuscate your code unless you have a really, really compelling reason to do that. And by obfuscate, I mean change the logic in such a way that it's no longer obvious what you're doing. Now, there are a few exceptions. If you have a very heavily used application, you might want to go in there and really hack that kernel that accounts for most of the runtime, but make sure that it is that it's well documented. Which gets to the next point: document all of your changes, especially if the new code looks significantly different from the original. Easiest way to get performance is to use optimized libraries whenever possible. If you're writing your own code, and it depends primarily on a linear algebra routine or an eigenvalue solver or these other common operations, if you can use the optimized libraries, just go ahead and do that. That's going to save you a lot of work. And I'm not going to say that nobody here, say, is an expert in eigenvalue solvers or linear algebra, but that's probably not your focus. I recall that most of you are coming from social sciences and computational chemistry and astrophysics. You're domain scientists. And the groups that work on these optimized libraries, that is what they do. Some of them have been involved in this research for many decades, and it's going to be hard to compete with them. And then finally, understand the capabilities and the limitations of your compiler, and we're going to see this as we go through a few of the examples. Then, how much effort should you put into optimizing your code? So this is going to depend on a number of factors. Is the code heavily or widely used? So one of our instructors this week, Andy Getz, is one of the key developers of the AMBER molecular dynamics code, which is very, very widely used. So those folks should put a lot of effort into squeaking out every last bit of performance. Similarly, does the code consume a significant amount of computer time? Next is the time to solution important? If this is a code that's, say, your lab's research code, and it really doesn't matter that much how quickly you solve the problem, you might not want to spend too much time on optimization. This can take a while. If optimizing your code, though, can help you solve new sets of problems, I'm going to say absolutely go for it. I did a collaboration with the San Diego Zoo a few years back where, using some of the techniques we're going to be talking about today, I was able to speed up the code by a factor of more than 1,000, and that completely revolutionized the kind of science they could do. Related to the previous slide where I talked about the linear algebra routines and eigenvalue solvers, as you optimize and profile your code, if you get to the point where most of that computing is occurring in routines outside of your control, so let's say you've written nice, clean, optimized code, you profile it, you find out that you're spending 99% of the time in an external math library, you're done. And then also think about the balance between time that you spend working on the codes and time that you spend doing your research. All right, so I'm going to say the first thing that you need to do, once you've decided that you need to optimize your code, is you need to profile it. As I mentioned, modern software can contain many thousands of lines of code, sometimes millions of lines, and you really need to know where to focus your effort. And often, most of the time is spent in a small number of routines. I find that this is actually pretty common. I've optimized and tuned a lot of codes over the years, and generally, you'll find that 80, 90% of the time is spent in just a handful of routines. So my go-to tool when I start profiling code is something called gprof. And this is, in terms of technology timelines, this is an incredibly old, venerable tool. It goes back to 1982, but it is such an excellent, easy-to-use tool that it's still extremely popular. Has a couple of advantages. First of all, it has universal support by all major C, C++, and Fortran compilers. To date, I have not seen a compiler that does not support gprof, and that includes Intel, Portland Group, GNU, the AMD optimizing compilers, and so on. It's very, very easy to use. There's a very shallow learning curve. All you do is recompile the code with the -pg flag. That's going to add some instrumentation to your code. You run the code. That's going to produce a gmon.out file. And then you just run the command gprof a.out, or whatever the name of your executable is, and then gmon.out. And it introduces virtually no overhead. So gprof, though, is not a tracing tool, and it's not going to identify bottlenecks in parallel codes. It will not tell you, when one process is sitting idle, waiting to receive data from another one. To do that, you're going to need to use more sophisticated codes. But if you want to understand the behavior, of that underlying serial code in your parallel application, I think gprof is absolutely fantastic. Okay, so why should I profile? I think I've kind of covered this already, but we need to determine what portions of your code are using most of the time. If you have an application with thousands to millions of lines of code, and you just start at the first routine and work your way through, you're going to be wasting a lot of effort. Um, and sometimes you want to go a little bit further, and I don't think we'll have time to cover this today, but I do have slides in the supplementary section where we talk about something called uprof, which is going to go into much more detail than gprof. It can give you access to things like, oh, excuse me, plane overhead. Okay, it will give you access to things like cache misses and mispredicted branches. So that's really going much deeper. Something that, say, the computer scientists would be a little more interested in, but worthwhile if you're really trying to figure out why a chunk of code is taking so much time. So we're going to start off with gprof. It gives you two types of output. It gives you a call tree and a flat profile. So the gprof flat profile is a simple listing of the functions and the subroutines. Functions if you're working in C, subroutines if you're working in Fortran, ordered by their relative usage. And as I mentioned earlier, it's often only a small number of routines that account for the large majority of the runtime. So gprof is incredibly useful for identifying hotspots in your code. So this is a profile from a real application. It was part of a collaboration that I did with the J. Craig Venter Institute, which is just on the corner of the UCSD campus, and I guess in the process of becoming part of UCSD. This was for a flow cytometry application. It's a technique used frequently by immunologists to sort cells into different classes, B cells and T cells, and various subpopulations of those cells. And give me 1 minute, I just want to turn off my email so it stops pestering me. Okay, so back. So when I profiled this code, I found that that a routine called get number packed data accounted for the largest fraction of the usage. So if I go over to that first column, you'll see that it's labeled percent time. We see that that first routine, get number packed data, accounted for about 68% of the runtime, followed by the function main, which was 13%, followed by quicksort double, which was 11%. In the next column, we'll see what we call the cumulative seconds. So that's how much time was spent by that routine and all of the routines above it. Of course, that's going to grow as we move our way down the table. The next column after that is what's called self seconds, and that's the amount of time actually spent in that routine, as opposed to the time spent in routines that are called by that routine. Next, you'll see the number of calls. In this case, get number packed data was called 399,587 times. The milliseconds per call and the total milliseconds per call. And you'll see that there's nothing listed for main, since that is not called by any other routines, and it's just executed once. gprof also gives you a call graph, and this gives you additional levels of detail, such as the exclusive time spent in a function and the time spent in all of the children, so functions that are called, and statistics on calls from the parent. I find that I don't have to go to the call graph as often as I go to the flat profile, but there is some useful information in there, particularly if you see that functions or routines are being called from multiple places, that might give you opportunities to say avoid unnecessary calls. So going back to my original code, for the call graph profile, we start at the top with main, and you'll see that main and all of its children accounts for 96.9% of the runtime. Now, usually these numbers won't quite add up to 100%. There's a little bit of overhead. There's some sampling that's involved, but it should be very close to 100. You'll notice that under main, there are a number of routines that are listed, and they are indented. So that indicates that these routines are called by main, and main in particular calls get number packed data, is hump, quick sort, radix sort flock, and ID2 center underscore all. Those routines are also labeled by the by the amount of cumulative, how would I put it? But by their inclusive runtime, so themselves and the functions they call. You'll notice under the called column, there are two numbers. The first number is so to get it straight, I believe that the first number is the number of times that routine is called by the calling routine that we're looking at. And then the second number is the total number of calls. In this case, it's pretty simple. We'll see, for example, that get number packed data is called 399,587 times, and that all of those calls are made from main. If we go down a little bit further, let's take a look at the bottom of the table, is hump. You'll see that main appears above it, and it's indented. That indicates that it is a routine that is calling is hump. And then below is hump, we'll see the three routines, get nearest events, pack arrays, and pack points, that are actually called by is hump. Once you start optimizing your code, make sure that you go back and you reprofile. So this was a case where we were able to optimize get number packed data so well that it's now no longer the hotspot. It's reduced down to having only using 20%, 26% of the time, and now main has risen to the top. So in this case, now that we're done optimizing get number packed data, we'll probably want to go back and optimize main. And by doing this, by going through several cycles of profiling and optimizing, I believe we were able to get this code running about 20 to 30 times faster, and that's not including any speed up that we get from going parallel. So that's just the speed up of the underlying serial application. So now we are going to do a hands-on exercise. Let me stop sharing so I could bring up my terminal. So we're going to go back to taking a look at the slides again. So you want to go into the profiling/time-based sampling directory. So from here, I'm going to go into performance, and then into profiling, and into time-based sampling. And you're going to see code in that directory. Very simple example. We have a main program. This is written in Fortran, but I think even if you're not a Fortran programmer, it will be simple enough that you could follow along. We have a main program. It calls two subroutines, and it will make two calls to subroutine 1 and one call to subroutine 2. And then these subroutines will make n calls to function F1 and function F2. And we're going to build this. We're going to compile with the Intel Fortran compiler with the PG flag so that we get the instrumentation for gprof. We're going to set our architecture -march equals core-avx2. This is one of the things that you need to do with the Intel compiler in order to get the AVX2 instructions. And then we're going to compile it two ways. both with the default inlining and with the inlining turned off. So if I look in the commands gprof file, you'll see that we have everything that we need in order to do this example. And Cindy, does the font size look good, or should I increase that a little bit more?
Just a little bit more, just to play it
Okay.
safe.
All right. No, let me go one more.
Thank you.
Oh, you're welcome. Okay, so the first thing we're going to do is in the script, we're going to load the Intel compiler. And then we're going to execute, we're going to compile the code using -03 and all of the things that come along with it. Then we're going to time the code, and then we are going to, after we execute it, we're going to run the gprof command, and we're going to take the output and we're going to dump it into a file that I'm naming profile intro inline. And then we're going to recompile again, and this time we're explicitly going to turn off inlining. And we will time again, and then we'll run gprof on the version of the code, with no inlining. I'll explain what inlining is in just a couple of minutes, and dump that into a profile intro no inline. So let's have everybody go ahead. Pretty straightforward. Just execute that commands file. So you could, since it's already executable, just /commands gprof. And that should only take a minute or so to run. So go ahead and do that. And let me know if you have any problems. And after you're done running that, assuming that you're doing the exercises, just go ahead and give me a thumbs up to let me know that it worked. All right, good. I'm seeing a lot of thumbs up. That means the reservation was working and I didn't screw anything up with permissions. Oh, I am seeing a... Okay, all right, good. That changed to a thumbs up. Excellent. All right. Narendran, I see that you have a red X next to your name. Did you run into a problem? No, good. All right, excellent. All right, so we're going to go ahead, look at the slides again. And what I love about this example is that, yeah, and if you're interested, that this is what the code looks like. This program is named intro. It allocates a few arrays. Here, if you're not familiar with Fortran, the equivalent in C would be malloc. We call subroutines 1 and 2. The 2 calls to sub 1 have a different order of the arguments. Then we deallocate at the end. And then our subroutines will take these arrays and it will do a loop over the elements where it calls function 1 and function 2. And then subroutine 2 just does something a little bit different. But the real work is done here in the functions f1 and f2. This code doesn't really do anything except take time. It's just a mix of square root and division operations. So when we profile that code, and everybody should take a look at the Um, at the profile intro inline file, you will see the you'll see the output, and not a lot of information in here. It just tells us that the program main took 5 seconds to run, and 100% of the time was spent in main, which is a little surprising because main does not do very much. All it does is allocate a few arrays, call a few subroutines. So what happened was basically we saw no usage for sub1, sub2, F1, and F2. And if the timings that you're seeing in the slides are different than what you're actually getting, keep in mind that we're running a smaller problem during the workshop just so that it will fit into your portion of the shared node. So the first lesson here, in addition to learning about gprof, is that an optimizing compiler is going to make transformations to your code that render it unrecognizable. So you probably got a hint, since I've been talking about inlining and turning off inlining, that what the compiler did in this case is it took the body of the code, say that function 1 and function 2, and instead of having a loop over calls to that, it took that body of the code and it moved it directly into the subroutines, sub 1 and sub 2. In addition, sub 1 and sub 2, since they were so simple, were also inlined into the main program. So what I'm going to end up with, even before the code is, say, compiled, there's going to be a rearrangement internally of the source code so that this looks like one long routine with everything inlined, and there is, as far as gprof is concerned, there is no longer an F1 and an F2, or a sub 1 and a sub 2. So if you ran that script, you would also see that we have an output file called profile intro no inline, and I'll go back here and open up that one. And here things look a little bit more like what we expected. You could follow along on either the slides or in your output file. In this case, we'll see that F1 now accounted for almost 40% of the runtime, F2 for about 26%. And again, it's going to vary between you running the example with this smaller problem size versus the original problem size. But followed by F2, followed by sub 1 and sub 2, and a little bit of time in main. So in this case, we explicitly turned off inlining using the dash inline level equals 0 flag. And now results are looking more like what we expected. And then as we go down to the call graph, we'll see that main calls sub 1 and sub 2, which in turn call F1 and F2. And want to point out here that down in the call tree, we could see that in this case, of the 3 billion times that F1 was called, sub 1 called it 2 billion of those times. Another quirk here is that the time reported for the entire program using the Linux time utility, you might have noticed, does not match what we see in the gprof output. So although gprof did a reasonably good job reporting where the time was spent, for truly accurate timings, there's no substitute for measuring directly. And by that, I mean using the Linux time command. Let me just go back into commands gprof. So that is just putting that Linux time command before your executable name, or inserting instruments into your code, basically timers, where you're keeping track of the time before and after blocks of code. I should add that gprof really doesn't add much overhead. Again, these are the timings that I got with with the larger problem, but it should hold for the smaller problem we're working with today. Um, this table here shows the runtimes with and without gprof profiling, and with inlining enabled or inlining disabled. And we see that in both cases, that the whether it's with or without inlining, that using gprof has very, very little impact on the runtime. And in fact, what you're seeing there in the inlining disabled column is probably a little bit of an exaggeration, just because of the nature of this call the nature of this code, that we're making these 3 billion calls to a routine that takes very, very little time. But even in that extreme case, we see that gprof adds very little overhead. All right, so we're not going to do this now. I'm going to say this could be your homework problem. I'm going to say go in, modify those functions F1 and F2 in intro.f to use sine and cosine and log functions. It's probably going to take longer to run. These trig functions, log functions are computationally expensive. And you may see some unusual things in the gprof output. Functions that are labeled or tagged with svml. So I won't tell you what that is, but maybe do a Google search. Another thing that you can do is take intro.f and break that into multiple files and rerun gprof. And figure out what does that tell you about the compiler's inlining capabilities. So you could take intro.f and you could break it, say, into 2 files, a main.f and a library.f, which contains sub1, sub2, f1, and f2. Or you could break it into 3 files, main.f, say subs.f that has subroutine 1 and 2, and funcs.f, f1 and f2. And you can also explore other compilers, the AOCC Flang or the GCC G-Fortran compiler. Like I said, I'm going to leave that as homework since we have a lot of things to do, but I think it will give you some additional insights into what the compiler can do. I'll give you the punchline. As you break this up into multiple files, the compiler will not be able to do the inlining. That's a little more complicated. That's something called interprocedural optimization. It's kind of hard for the compiler to look across multiple files for these inlining opportunities, but it is an active area of research, and I've seen some compilers in the past that have tried to implement that. So it's been 40 years since gprof came out. You might be wondering, is there anything new? We have a tool installed on Expanse. It's called AMD uprof or muprof that can give you a lot more detail than gprof, including low-level information on cache misses, branch mispredictions, etc. I say we'll talk about this later, time permitting. We probably won't get that today, but the directories, the profiling directory, does have uprof examples in there, and I have some slides at the end of this presentation. So this has really been shortened down from a roughly a half-day talk to fit into a 2-hour or so time slot. Okay, so we're going to talk about actual strategies that we can use for tuning your code. We're going to give a little bit of background on the memory hierarchy and effective use of cache. We'll talk about loop level optimizations, something, and I'm sure there's a more technical name for this, but I call it optimizing for the common case, force reductions, and interprocedural optimizations. So before we get into any specific techniques, we're going to talk a little bit about the memory hierarchy and the difference between memory-bound codes and compute-bound codes. So in a memory-bound code, it's going to be the rate at which data can be delivered to the CPU that's going to be the limiting factor. When we have a memory-bound code, our goal is going to be to apply cache-level optimizations so that the CPU is not starved for data. For compute-bound codes, in that case, the performance of the processor, the clock speed, the number of math operations it could do per cycle is going to be the limiting factor. So in these compute-bound codes, data can be delivered fast enough, but the processor can't keep up. And our goal is going to be for a compute-bound code to reduce the amount of computation done on a given piece of data. What we're going to find, though, is in real applications, we're often dealing with a combination of compute and memory-bound kernels. So I'm just going to back up a little bit here, and we're going to look at the code we had been working at. I'm going to say this is a classic example of a compute-bound code. So for each bit of data, we're doing a lot of work. For example, when we call function 1, it's going to be a square root of a number divided by another square root plus the division of two numbers. Once we replace some of these square roots with sines and cosines and logarithms, it's going to become even more expensive. And we're going to be doing a lot of work for each of the for each piece of data. We're going to be the next example, though, we're actually going to run is going to be the opposite extreme, and that's memory bound, where we're reading in data and doing very, very little work on it. And this is where the cache level optimizations are going to come in. So some of you may have seen figures like this. It's the computer memory hierarchy, often drawn as a pyramid. As we go to the top of the pyramid, the memory or the storage is faster, but it's much more expensive. And at that very top, we have what are called registers. These are on the CPU. They hold pieces of data that are immediately accessible in the next clock cycle by the CPU. And once we get data into the register, we'd like to reuse it as much as possible. Registers are very, very limited. I've lost track of this, but I believe that registers are, I think under 100 registers per CPU core. So very little is going to fit into register. The next level in the hierarchy is the L1 cache. And L1 cache is small. This is going to vary by the processor, but it's typically on the order of about 10 kilobytes, which is tiny. But data that's in the L1 cache could be accessed very quickly. So data in registers is available on the next clock cycle. L1 cache is on the order of nanoseconds, so a few clock cycles. Then below that, we have the L2 cache, which is larger, typically a few hundred kilobytes. A little bit further away, it might take nanoseconds, or given a 3 gigahertz clock speed, 10 nanoseconds would be about 30 clock cycles. So having an L2 cache isn't bad, but it's definitely worse than having the data in L1 cache. And then you go further out, and we have an L3 cache, which is typically tens of megabytes. And a little bit further away still, L1, L2, and L3, these are all part of the processor hardware. They're right there on the die. It accounts for a lot of that, for a lot of the transistors on that die. Now you might be wondering, why don't we just build more L1 and L2 and L3 caches? And these have been growing over the years, but it's very, very expensive. It's part of the fabrication process, and you can only get so much cache on that die. Then beyond that, we go out to DRAM. So this is what you think of as main memory. This is going to be in the order of tens to hundreds of gigabytes. If you're working on Expanse and you had an entire node to yourself, you would have access to 256 gigabytes. Since we're sharing, I believe our reservation gives you access to a quarter of a node. So you'll be able to access 64 gigabytes. And then finally, at the bottom of the hierarchy is external storage devices. And that could be solid state drives. In our case, we have one on each of the compute nodes. Very fast compared to the hard disks. So access time is on an order of 100 microseconds compared to milliseconds, going all the way out to hard drive, but still very slow compared to spots higher in the data hierarchy. So essentially, we go at the top from fast, small, and very expensive to slower, larger, and cheaper. And um, in order to get good performance out of our code, particularly memory-bound codes, we need to take advantage of two cache essentials. Now, if you're a computer scientist and you take your hardware class, you are going to go very, very, very deep into cache. You'll learn about cache architectures and replacement strategies and so on. But for application developers, you really just need to know these two things. There's temporal locality, which we try to exploit, and that means that data that was recently accessed is likely to be used again in the near future. So in order to take advantage of temporal locality, once we load data into cache, it's going to remain there until it has to be pushed out to make room for new data. So if we go back to our hierarchy, let's say that we are processing 10 gigabytes of data that fits in the main memory. 10 gigabytes is obviously much, much larger than the L1, L2, or L3 caches. We need to move it into cache before it could be used by the CPU. But since it's so much larger, that 10 gigabytes is so much larger than any of those cache levels, whatever was in there earlier is eventually going to have to be pushed out. But again, if we put something into cache, we'd like to use it as much as possible. Now, spatial locality, the idea behind this is that if a piece of data is accessed, it's likely that neighboring data elements in memory will also be needed. So to take advantage of spatial locality, cache is organized into lines. I say here, typically 64 bytes. In fact, every processor I've ever seen has cache lines of 64 bytes, although I'm sure that there are special purpose processors, maybe processors used in embedded computing that are a little bit different. But for HPC systems, you are going to see 64-byte cache lines. And we don't load just that piece of data we need. We load the entire cache line. So our goal in cache level optimization is very simple. We are going to exploit these principles of temporal and spatial locality to minimize data access times. And before we go on, do we have any questions? Oops.
No questions in the chat.
Okay, great, thank you. All right, so moving on. So we're going to start with one-dimensional arrays. This is a little example, little snippet of C code. So a one-dimensional array is stored as a block of contiguous data in memory. So let's say that we decided to allocate an array of 100 4-byte integers. So we use the malloc command. We cast it to an integer pointer. We allocate 100 of these integers. So in memory, we don't know what the absolute location is in memory, but we know the relative location of these pieces of data. So starting with an offset of 0, we have our first element, x of 0. And then offset by 4 bytes in memory is x of 1, and then x of 2, x of 3, and so on. So when we're working with 1D arrays, cache optimization is very, very straightforward, and you're probably going to write optimal code even without trying. When possible, just access the elements in order. So I show a simple loop here where I'm taking each of those elements of the array x, and I'm incrementing them by 100. So I have my for loop, I equals 0, I less than n, I plus plus. So element by element, I am updating the values of x sub I. So what's going on with regards to cache? So again, assuming 64-byte cache lines and 4-byte integers, we're going to start off, our cache is going to be empty. We're not going to have any of this data in cache. I'm going to take elements x0 through x15, and I'm going to load them to cache. So those 16 4-byte elements are going to fill a cache line. And now I'm going to increment element 0, element 1, element 2 through element 15. Then I get to element 16. It's not available. So now I'm going to load another cache line. I'll load x of 16 through x of 31 into cache, and then I'll increment those elements. Now, in reality, and this is Well, one of the really advanced features of modern processors is that they can recognize the pattern of data access and prefetch the cache line, next cache line before it's needed. So in this case, while I'm working on elements 0 through 15, I've gone through a few iterations of that loop. There's logic within the processor that says, hey, I kind of figured out what we're doing. We are accessing these elements in order. So I'm going to, if I could, if the memory bandwidth allows, I'm going to get that next cache line ready. In this case, the processor is probably going to be starved for data because we're doing so little work on each word. But if we were doing a more complex operation on each of these elements, say instead of incrementing by 100 but calculating sines and cosines and logarithms and powers, in that case we would be CPU limited, and it would be nice to have that data in cache ready for when we need it. Now, one of the questions that often comes up at this point in the talk is, do I have control over cache? So, for example, can I say, Okay, can I say I want to load a particular location memory into cache? So you don't. Modern processors directly implement advanced cache replacement strategies. They do branch prediction, they do the prefetch. You don't have control over that. Again, maybe in some embedded computing applications, where you're actually designing the hardware and you're working at the very, very low level, you might be able to. But on HPC systems using standard languages, you're not going to have that level of control. So the best you can do is to follow standard practices to exploit the temporal and spatial locality, and in some instances, choose optimal parameters based on your cache sizes. So now we're going to switch to something a little more complicated, and that is multidimensional arrays. So pretty much every modern language gives you a way to write a multidimensional array. This is really handy if you're doing, say, computational fluid dynamics or magnetohydrodynamics, climate or weather, something where you're solving a problem on a grid. It's much easier to think in terms of a multidimensional array. But from the computer's point of view, there is no such thing as a 2D array. It's what we call syntactic sugar, and it's provided as a convenience to the programmer. So under the hood, those multidimensional arrays are just stored as linear blocks of data. And this is one of the biggest sticking points when it comes to performance, is unfortunately, there are two conventions, and neither of them, I think, is ever going to change in our lifetime. You could think of this as driving. In the US and Canada and most of the European mainland, we drive on the right side of the road. In the UK and India and Australia and the former Commonwealth countries, and I believe Japan, they drive on the left-hand side. We're pretty much stuck with that. It's unlikely that any country is going to change their mind and say, come over to the other side. And that's the same situation with programming languages. They fall into two big categories: column major order and row major order. So column major order is what you're going to see with Fortran, R, and MATLAB. So if I have this multidimensional array, the first or the leftmost index is going to vary the fastest. So if I have this 2D array, I'm going to be going down the columns. So it's going to be, and when this is laid out as a 1D structure in memory, it's going to be 147, 258, 369. Row major order uses the opposite convention. Here, the last or the rightmost index varies the fastest. And you'll see this in Python, Mathematica, and C or C++, and any of the C-like languages. So again, taking that same 3x3 array, in this case, we're going to be going across the rows. So it'll be 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's how it will be stored as that 1D structure and data. So what this means is I have to be careful how I write my loops, in particular my loop nesting, when I work with these multidimensional arrays. So on the top, I'm showing properly written Fortran code where we are adding two arrays element by element. So you'll notice we have the outermost loop is over j, the innermost loop is over I, and then we're calculating zij equals xij plus yij. If this were C code, um, I would need to flip those loops around. So my outermost loop is going to be over I. I've got the for I. The inner loop is going to be for j, and now I have my zij equals xij plus yij. All right, so in the next example, we're going to be compiling C or Fortran codes using the Intel compilers and the AMD compilers. So the Intel is going to be the ICC and iFort. AMD AOCC compilers are going to be Clang and Flang. And we're mainly concerned with the compiler flags that control the overall optimization level and the target architecture. So the table on the left shows the different optimization levels. If we do not specify an optimization level, the result can vary. And we'll see an example of that once we get to the matrix addition case. -0 means that we want absolutely no optimization. This is going to give you terrible performance. There might be times when you want to compile with -0 as you're developing your code or trying to figure out what the compiler is doing, but you would never do this for a production run. -01 gives you some limited optimization. Again, it's less than what you will typically want. -02 is what we call moderate optimization. It will do a lot of the restructuring your code as long as it does not potentially change any of the floating point results. And then -03, which is aggressive, which is what you're normally going to use, allows the compiler to reorder math operations. Now, if you're familiar with floating point arithmetic, you may know that what we call the algebraic identities are not necessarily floating point identities. Floating point numbers can only be represented to a finite number of places. There's going to be a little bit of round off every time, and that's going to depend on, say the order of the additions and multiplications. Generally, you'll want to use -03, but you'll always want to use at least -02. Another thing we need to do when we compile the codes is we need to make sure that we are getting access to the most advanced instruction set. So there's things called AVX and AVX2, and I believe you heard about these the other day, which allow you to do 8 or 16 math operations per cycle per core, but you only take advantage of those advanced instructions if you specify the target. So for the AMD compilers, we'll need to have -march equals ZNVER2. That's for the Zen 2 architecture. For Intel, we're going to need -march equals core -AVX2. So now we're going to go to our next hands-on example. Let me go ahead and go back to my terminal again. So in this case, we're going to go into performance. We're going to go into performance tuning. And we're going to go into matrix addition. And you'll see there are two scripts in here labeled commands _2d add _AMD or _Intel. And we'll take a look at one of those. So for the AMD version, we start off, we're going to do a module load AOCC so that we get the AMD compilers. We're going to be compiling a Fortran, piece of Fortran code using the Flang compiler. We're going to set the architecture to the ZNVER2. And then when it comes to the optimization level, I'm going to try this with the default, with O0, O1, O2, and O3. And each of these times, I'm going to keep track of my executable. So I'm going to have, depending on the optimization level, I'm going to have underscore df for default, underscore O0, O1, O2, and O3. You'll also notice that in the name, I have underscore good, or I have underscore bad. And by that, I mean in the dmad good file, we have the loops nested in the proper order. In the dmad bad file, we have the loops in the opposite order. So let me just go into one of those. So let's take a look at dmad good. So up here, we're just allocating a few arrays. We're initializing the arrays. And actually here you see an example of using timers. In Fortran, I can call the system clock routine. I call it before clock 1, after and clock 2, and then I calculate the elapsed time. And there's a function, I think down, yeah. And there's a function down here to do the math. And then the actual work is right here. It's going to be these 5 lines where I am adding those arrays element by element. Now, if I go into the other file, into dmad bad, you'll see the code looks, sorry. See, the code looks the same, except I have the loops nested in the wrong order. So what we're going to do is pretty simple. You can simply execute. You can simply execute the commands 2d add underscore AMD script, and then execute the Intel script. And do this, ignore in the slide where I say 30,000. I actually reduced the problem size to 25,000 squared so that it will fit onto your portion of the node. And we're going to keep track of the runtimes. So run these, write down the runtimes, try not to look ahead at the next couple of slides, and then let's see if we can make sense of the results. So I'm going to run this, and all of you can go ahead and do the same. And give me a thumbs up when you're done. And I'll recommend, in those commands files, don't just, for convenience, you can just run it, /commands 2d add underscore AMD or Intel, but do take a look in there and make sure you understand everything I'm doing with the compiler options. All right, since I'm not hearing anything, we will move on. So we just ran the example. And the point of this is data access order really that important? Do we really need to care that much about cache level optimization? And I think the lesson here is going to be absolutely. So this is a classic memory bound code. We're reading the data. We're doing very, very little work on each byte of data. We're just taking one value from each matrix, adding them, and then storing them into another matrix. Now, the numbers that I'm showing on the slide are going to be a little bit different than what you got. This was for matrices of 30,000 by 30,000, which was great when I had access to a full node, and we scaled the problem back a little bit. But the general results are going to be the same. So what I'm showing here in these two tables, on the left was compiling the code with the proper and the improper loop nesting using the AOCC compiler, and on the right, same thing with Intel. And we have 5 different cases. We have the default, -0, -01, -02, and -03. And when we compare the proper and the improper loop nesting results for the AMD compiler, we see that if we have the proper loop nesting, that the code runs a lot faster. And that is regardless of the, it's regardless of um, the optimization level that we choose. So for example, if we look at the default or the -0, we see that with proper loop nesting, it takes about 3.5 seconds versus 9 seconds. With -01, we're down to 1.68 versus 5. For -02, 1.14 versus almost 5 seconds. Now, if we look at and another thing that you'll notice is that the default, the runtimes that we get for the default specify no optimization level, they're the same as when we get to -00. So that's really important. With the AMD compiler, by default, we get no optimization. If you look over here at the Intel compiler, something really interesting. When we use the default, we get runtimes that are the same as the O2 or the O3 level. In addition, at these higher levels of optimization, O2 and O3, it doesn't seem to care whether or not we have proper loop nesting. So we're going to see what is going on. So I mentioned this already. Runtimes improve for the AMD compiler as we enable higher levels of optimization. The default appears to be the same as disabling all optimizations, and the improper loop nesting is always slower. So, never rely on the compilers, the default optimization. Now, the Intel compiler is more interesting. Here we see, first of all, that default appears to be the same as -02. But don't count on this. This is not a standard. This is just what Intel does. In addition, look at the -02, -03, and the default lines. The runtime for the properly written and the improperly written code is the same. In this case, the Intel compiler was smart enough to recognize that loops are improperly nested, and it automatically reordered those loops in order to get better performance. Now, if you really dive in, if you would use, I believe, the -S flag, S is in Stephen, to generate the assembly output, and if you can read assembly, you would see that those loops are actually re-nested. So, the lessons here is, making optimal use of cache is really, really important when you have memory-bound codes. And sometimes the compiler will help you, like the Intel compiler, and sometimes it won't. So I show here, when we compile out -02 or O3, on the AMD side, you're out of luck. If you wrote those loops with the wrong nesting, you are stuck. On the right side, the Intel compiler, the compiler saved you from your bad programming habits. But I would say don't count on the compiler saving you. Sometimes it will, sometimes it won't. Okay, so which compiler should I use? Since Intel was able to fix my bad programming, shouldn't I just use it instead of the AMD compiler? So I'm going to say not necessarily. This was an extremely simple code, and the compiler could analyze it and fix it. But even with the Intel compiler, there's no guarantee as the complexity of the code increases that it will be able to recognize your bad programming habits. And then modern compilers do a lot of clever things to make codes run faster. They rearrange instructions, they do loop unrolling. We'll talk about that a little bit later. But the vendors optimize their compilers for their own hardware. So we find that for well-written code, AOCC is often a little bit better when running on AMD hardware, but you might find the opposite if you're running on an Intel system, and there are quite a few out there. In that case, again, try all the compilers, but you may find that an Intel compiler running on Intel hardware is going to do a little bit better. All right, with that, we've been going for quite a while now. I'm going to suggest that we take a short break and that we come back right at the bottom of the hour. So it's 1:22, and I will hopefully see everybody back at 1:30. So I'm going to get started again. So let's go ahead and share my screen. All right, so we're done with our short break. And let me go into full screen mode again. All right, so we talked about one one simple but very important case, and that was getting your loops nested properly. But we're going to go through a few of what they call loop level optimizations, loop fusion and fission, and something called loop invariant code motion, loop peeling and unrolling and blocking, and breaking out of loops early. And for lack of a better term, I'm sure that the computer scientists have a proper name for this, something that I just call short loop optimizations. So, starting with probably the simplest kind of transformation you could do to your loops, this is something called loop fusion. If we take two or more loops with the same range of iterations, we can combine them into a single loop. So in this case, on the left-hand side, we have a loop where we iterate over the elements of these arrays. They're all the same size. And we take element by element, x sub I times y sub I, and we add a sub I, and we store that in Z. And then that's followed by another loop where we work on those same elements, x, y, and a, except here we do something a little bit different. Here we take x sub I, and we add it to y sub I times a sub I. Loop fusion is where I take those two loops and I combine them into a single loop. And you can see what some of the advantages are going to be here. First of all, we don't have that overhead associated with the loop, but more important, this is going to allow for better data reuse. So given that Z sub I and W sub I both need to use the same elements of X, Y, and A, once we have them already in the top of the memory hierarchy, in fact, right there in register, we might as well use them again. So if we can take those two loops and we can fuse them, now once we've loaded X, Y, and A into the registers, we can use them twice. We could use it to calculate Z, and we could use it to calculate W. So with that, we're going to jump right back in to another hands-on exercise. So the fused loops and the unfused loops are going to combine, going to do element by element multiply add operations on these three arrays, just like I've shown, either in a single loop or in two separate loops. So we're going to inspect the code, make sure that you understand logic. You're going to compile these with the Fortran and the AOCC compilers with the different optimization levels like we did before. Ignore the next line where we say that we're going to run this with a rank of 30,000. We're going to be doing this with a matrix rank of 20,000 so that it fits into the memory allocated to your job. And we're going to keep track of the runtimes reported by the codes. So let me do this. I'm going to stop sharing. We're going to go to the, I'm going to go to my entire desktop again. Whoops, sorry. Oh, wrong button. Share. I almost left the meeting. Okay, so you should be, can somebody confirm that you're seeing my whole desktop again?
Yes, we do.
Okay, thank you, Cindy. So I'm going to go back to the top. And I'm going to go into performance, into performance tuning, and we're going to go into fusion. Right, so we'll take a look at the code first. So again, this is Fortran code. I know that more of you are probably familiar with C, but again, it's a very simple code, and I think you'll be able to follow along. Here's what I'm calling the guts of the code, where I've got my two loops, just like I showed previously in the slides, where I'm using combining X, Y, and A in various ways and saving that in Z and W. And then for the fused loops, a little bit simpler. I just took the body of those two loops and I combined them. Now, I want to point out something that may seem a little mysterious in the code. So I do these calculations. I initialize x, y, and a, and I do various combinations of floating point multiply adds to save the results in z and w. I've got this little bit of code at the bottom here where I test to see if z of 1, if the very first element is equal to -1. And then if it is equal to -1, I'm going to write out the results. Now the way I initialize those arrays, there's no way that I'm going to get -1. Now the reason I did this, and I haven't tested it recently with these compilers, is that some compilers will recognize that if you do calculations and never use the results, it will just optimize away the entire code, and you'll get a runtime that's very, very close to 0. You can go ahead. I have everything that you need in these commands files. So let's take a look at one of those. Look at the Intel. Again, I'm going, sorry, at the AMD. Again, I'm going to, there, I'm going to load the AMD compilers. I'm going to compile just like I did before. This is going to look a lot like the script that we had for the matrix multiply example. Again, using the Flang compiler, specifying the architecture, and then either default or various levels of optimization. I'm going to give each of those, binaries a different name, and I'm going to do this both for the fused and the unfused loops. So I'm going to say, go ahead, run those two examples, keep track of the runtimes, maybe poke around a little bit in the code to make sure that you understand what's going on, and then we will regroup in just a couple of minutes. And I'll get mine running, and after that, I'll take a look at the chat. Okay. I see. I'm looking here at the message from Mehmet. Make sure that you're doing this, and I think you figured it. Well, maybe not. Make sure that you're doing this on a compute node. So I mentioned earlier that we need to do the srun.shared command. If you don't do that, you're going to be working on the login node where your resources are going to be very, very limited. So, and Mehmet, I'll put that into the Slack, and I'll also put into the chat. And I think that should be enough time for everybody to run the examples. Give me give me a thumbs down if you're not done. Okay, I'm not seeing any thumbs down, so we will move on. Right, so well, we're now looking at the, no, let me go back to full screen for my presentation. So again, your results are going to vary because we were working on a smaller problem, but overall the um, the general findings should look like what I have here. Again, just like I did for the matrix multiply problem, matrix multiply problem. On the left-hand side, I have a table for the AMD Flang compiler. On the right, for the Intel iFort compiler. Same as before, for the AMD compilers, default optimization is equivalent to -0. But you'll see that when I actually, when I manually fuse those loops, that I'm getting a little bit better performance. So when I'm using a reasonable optimization level, say of 0.2 or 0.3, ran, in my case, for this larger problem, about 2.8 seconds instead of 3.6. So, a modest change, but what is that? That saves you, knocks about 25% off your runtime. We see the same kind of behavior with the Fortran compiler. Again, default is equivalent to -0.2. And in this case, we always see that manually fusing those loops resulted in a little bit better performance. And in this case, the AMD compiler did slightly better than the Intel compiler. But again, that's going to vary from code to code and also across AMD versus Intel hardware. Right, so, sorry, let me go back into full screen again. All right, there's another technique that we can do very similar to loop fusion, and this is called loop fission. And this is where we take a loop and we split it. And sometimes this can improve the performance. So we already know from trying this both ways that for this piece of code, that having fused loops is better. But sometimes if you have very, very complex loops with too many different data streams, in this case I mean arrays that we're working on, splitting the loop can improve performance. And it's often difficult to decide if the loop should be fused or split. The compiler will try to analyze your code and make a best guess. But if in doubt, and if this is a portion of code that's really, really critical, it accounts for a significant amount of the runtime, I would try both and see which is faster. In general, though, if it's going to be simple loops like we're working with now, they should be manually fused. Okay, one of my favorite optimizations is something called loop invariant code motion. And this is where you take a calculation that's going on inside a loop, and instead you pre-calculate the result outside of the loop and use that. So here's a case, really, really obvious. Let's say I have this loop over elements of array x and z. And for each element z sub I want x of I plus the square root of c, where c is some constant. And you can see that this is square root of c is an invariant. It's the same for every iteration of the loop. So we can just pull that outside. I could create a new variable, square root c equals square root of c, and I could then use that in place of the square root function. Now, a compiler, most compilers, for a piece of code this simple, are going to be able to recognize this, but I still recommend that you do it yourself because there is no downside, and you don't want to count on the compiler to fix your bad programming habits. But sometimes when we're working with nested loops, these invariants are going to be less obvious and may even be vectors results. So this is actually taken from a real life code, modified to for the presentation. This was the collaboration described earlier with the San Diego Zoo and the US Geological Survey. So we have triply nested loops, and we're doing a calculation that depends on 3 different positions, the x, the y, and the z. So you'll see within a loop, we do calculations on x sub I, y sub j, and z sub k. So we're taking data, we're making contributions to a 3D grid, and that is the array res. So in this case, res of I, j, k, and it has that dependency on x, y, and z. So if we look at this, we will notice, first of all, the scalar x2, y2 does not depend on the index k. So that means in that innermost loop, we're calculating that over and over, but we don't need to. Similarly, the square root of b times x2, y2 does not depend on the index k. So what we can do is we can take that calculation, x squared, and move it to the outermost loop nesting, because it's not going to depend on j or k. And then we can take the calculation of x2, y2, and then the square root of b times x2, y2, and we can move that into the up one level in the loop nesting. And now, by the time we get into that innermost loop, instead of doing all of these additional calculations, all I have to do is calculate the exponent minus a times z squared, and then multiply it by this term that I had calculated already, which is going to be the same for every iteration of the innermost loop. But we can take this a step further. We'll notice that z2, or z squared, does not depend on the indices I or j. And of course, the exponent of minus a times z2 does not depend on I or j either. So what we can do is a little bit more complex in loop invariant code motion. In this case, we can pre-calculate a vector that I'm going to call z term. Pre-calculate that, move that outside of this triply nested loop, and then in the very inner loop nesting, I can just call that term z term of k, and then multiply it by the square root of x2, y2. And by doing this, we are going to make our code a lot faster. So in fact, pre-calculating this, it reduces the number of exponential evaluations from to nz from nx times ny times nz. So we have reduced the amount of work calculating those exponentials by a factor of the horizontal grid dimensions, nx times ny. And this is something that was actually implemented in the code and resulted in a tremendous speed up, since exponentials are very expensive to calculate. Another technique is something called loop peeling, and this is where we recognize one or more iterations within a loop are special, and we can handle them as a one-off instead of say doing a test inside the loop. Excuse me. Okay. Sorry for that. And sometimes loop peeling can then be combined with loop fusion. So here's an example where we have two loops. The first one is over I equals 0 to n. The next one is over I equals 1 to n. And within that first loop, we have one special case. If I is equal to 0, we do something different. We calculate x of I divided by y of I. But that only happens once. So what we can do is we could take that special case, we could pull it outside, we could calculate z of 0 explicitly, then change that loop so that it starts at iteration 1 instead of 0. And now we also have two loops with the same bounds, so we can combine them into a single loop. So this was a classic example of loop peeling followed by fusion. But even if you don't have those two loops to fuse, just taking that special case and pulling it outside so that you don't have to do that logical test each time is going to give you a big speed up. There's a technique called loop unrolling, and it's very powerful, where you take the body of the loop and you replicate it, and then you modify the stride. And this optimization can help the processor make much better use of what they call the arithmetic units, the pieces of hardware that do the additions and subtractions, divisions and square roots. Essentially, you're making the loop more complex, which may seem like a bad thing, but it gives the compiler a lot more instructions to work with so that it could reorder them and get better performance. So in this case, I had a loop, I equals 0 to 1024, where I'm simply adding x and y element by element and storing them to array z. In loop unrolling, I'm going to take the body of that loop. In this case, I replicate it 4 times. I calculate zi, I plus 1, I plus 2, I plus 3, and then I set my stride to 4. And this is generally going to give you a lot better performance. But I will warn you, though, that this is an optimization that you probably don't want to try yourself. Optimizing compilers are really, really, really good at loop unrolling. And if you manually unroll your loop, it's going to make your code a little bit uglier, a little more difficult to maintain. And you can see that I'm going to need to explicitly write some cleanup code. In this case, if my number of iterations was not divisible by 4. So again, I would avoid manually doing loop unrolling, since the unrolling depth is going to be highly dependent on the processor architecture. But in some rare cases, you can actually beat the compiler. So that's why I want you to be aware of this technique. I had worked on a chemistry application, actually with a collaborator here at UCSD a few years ago, where he had these incredibly complex loops. So I'm showing one here where the original loop was I equals 0 to 4319 with a stride of 2. And what I did was, instead of using the original loop, I unrolled this by an additional factor of 4. Now this loop was really and incredibly complex. It was code that was not written by hand. In fact, it was automatically generated as a fit to some quantum chemistry results. And there are many loops like this within the functions. I even have a line here that shows several hundred lines of code not shown. It was so much code, it was so complex that the compiler couldn't figure out what the best unrolling was, so it just gave up. I was able to do it by hand, but I'm going to say in 25 years of doing this kind of work, this was the only time I have ever been able to unroll a loop and beat the compiler. There's another technique. There's probably a more technical name for this, but I haven't been able to find it. And that's what I call just breaking out of a loop early. This gets to be a little more difficult because it's going to require that you understand the semantics of your code. So this was from a computational finance collaboration that I did with the University of Illinois. Stripping this way down, there was a loop, I equals 0 to n, where for each element of y, if y sub I is less than a constant, I do some stuff. And if it's not, then I continue on to the next iteration. Now, this was a case where I was able to use my knowledge of the code and the fact that the elements of array y are monotonically increasing. So that is, we are absolutely guaranteed that y sub 0 is less than y sub 1, which is less than y sub 2, which is less than y sub 3, and so on. The array, I believe, actually corresponded to timestamps. So the compiler has no way of knowing what is that array y. So it's only with our domain knowledge that we were then able to implement an additional optimization. Because once y is greater than equal to the constant the first time, it's going to be greater than equal to the constant for all subsequent elements in the array. So in that case, we're often, by putting this small change, we're able to break out of the loop early and get a really big speed up. So this is the case where The compiler only understands the syntax of your code and cannot do this optimization for you. And then I have something that I call optimizing for the common case, and this is getting a little bit more complicated, but we had got a big payoff from this. So this was from a collaboration I did with NCAR, National Center for Atmospheric Research. They had a new global climate code called MPAS, Model for Prediction Across Scales. Collaboration between NCAR and Los Alamos National Lab simulates atmosphere, ocean, and other systems all coupled together. In this case, instead of using a rectangular grid, they use an unstructured grid that is composed overwhelmingly of hexagons, plus a very small number of pentagons and heptagons. So you can prove mathematically that you can't entirely cover a sphere with hexagons. You'll need, I believe that you'll need at least 12 pentagons in there. But in this case, out of the many, many thousands of grid cells, vast majority, 99.99%, were hexagons. And we were able to take advantage of this fact. Again, us knowing the semantics of the code, whereas the compiler can only understand the structure, the syntax, where we had a loop over all of the edges for each cell, whether or not it was a pentagon or hexagon. So what we did was we split out the code. We wrote a special block of code for hexagons. When we can test each cell, see, is this a hexagon? Good. We're not going to iterate. We're not going to have a loop over the edges. Instead, we're just going to write this special piece of code. And then we'll have the default code that picks up those small numbers of pentagons and heptagons. And that was able to give us a really big speed up. I believe this chunk of code ran, this particular piece maybe 40% faster, which, given that this is a global climate code that's going to be running on thousands of nodes, we consider to be a really big win. Okay, I'm going to talk about one more type of optimization, then we'll do another example, and this is something called force reduction. And a force reduction is when you replace an expensive operation with an equivalent, less expensive one. So exponentiation operations, especially a floating point base raised to a floating point number, is incredibly expensive. The trig functions, logarithms, and so on are expensive. So I'm going to say, if you know an exponent at compile time, instead of calling the power or the exponentiation function, you can just write out a series of multiplications. So in this case, x to the 8th power, I could calculate x squared, and then x to the 4th from x squared, and then x to the 8th from x to the 4th. Doesn't come up too often, but sometimes you'll have to raise bases to a fractional power, say like the 1.5 power. And if I could take pow of x comma 1.5 and rewrite that as x times square root of x, I'm going to get a lot better performance. Place where you might find better use for, or more common use for force reduction, is with trig functions. So go back to your high school math. If you have a code that does a lot of trigonometry, see if there are ways that you could rewrite it. So for example, if I had a sine x times a cosine x, that's equivalent to 1/2 times the sine of 2x. Where I have sine x cosine y plus cosine x sine y, that's equivalent to sine xy. In the first case, I've gone from evaluating two trig functions to just one. In the second case, I've gone from four trig functions down to one. So I could get a lot of speed up there. There are some other tricks that you could do. Just make sure that you test this thoroughly, and that you make sure that any identities that you apply to all four quadrants. So for x and y, both positive, both negative, and x or y, one positive and one negative. So lot of opportunity for speed up. Also look for hidden opportunities for force reductions. This is often going to come up in logical tests that could be written in more efficient ways. Think about what results are really needed. This is again taken from real life example, where let's say I have a loop over over elements of x. I have my for I equals 0 to n, and then I want to test, is log of x sub I less than a constant? And if so, I'm going to increment a counter. Well, when you think about it, we don't really need the logarithm of x. We're just comparing log x to a constant. So what I could do here is, instead of comparing log x to c, I could instead compare x to the exponent of c, so e to the c. So I could take expc, define that as the exponent called to c, and then use that within my loop. So now we can avoid that expensive logarithm calculation and just do a simple comparison. And with that, we are going to do one more exercise. So let me go ahead and get my entire screen shared again. So I'm going to, in this case, I'm going to go into the performance directory. I'm going to go into performance tuning and into force reduction. And in this case, I'm going to, let's take a look at the code. And the real guts of the code are, go down here. We're looking at C code in this case. Just a minute. So what I've done is I've filled the arrays x and y with random numbers be between 0 and 1. You could think of these as representing points in a plane. And I want to find every pair of points, count how many points are within a cutoff distance of each other. We're going to call that a distance del. So here I'm going to be looping over looping over I, looping over j. I did a little trick here so that I don't have to do so that I don't double count. So I have 4i equals 1 to n minus 1, and then j equals I plus 1 to n. So this way I'm explicitly considering each pair of particles once, and of course avoiding the case where we're comparing a particle against itself. And then we calculate the squared distance between those particles. And then we want to see, is the square root of that distance less than some cutoff? Here we called it del. In the case where I did not have force reduction, in the case where I do have force reduction, I'm a little clever, and I recognize I don't really need r. I just need r squared, and I can compare that to the cutoff squared. So with that, again, if we look in the commands files, we'll see that for AMD, we first load the AOCC compilers. We compile this time with Clang, which is the AOCC C compiler. We build the code, with and without the force reductions. We give each of those executables different names, and then we execute them, where the first number is the number of particles and the second number is the cutoff. So I'm going to say, go ahead, execute these codes with both the AMD and the Intel. If the AMD takes long, You don't need to do the second case. So let's execute that. Keep track of the runtimes, and they're reported by the code. And this problem doesn't use that much memory. So if you're interested, you can go in there and tinker with different values of n, different values of cutoff. I think that the ratio of the runtimes for with and without force reduction is going to be pretty consistent though. And I'll just give you a few minutes to do that, and maybe wait about 2 minutes, and then we'll see if anybody had gotten stuck. All right, so I'll go on to the next slide. Let me just go back to full screen again. Okay, so you should have gotten results that look something like this. You know, when we did the force reduction, we compared the square of the distance of the particles to the square of the cutoff. And without the force reduction, we actually compared the distance between the particles to the cutoff. And you can see we got quite a speed up. It's almost a factor of 3, because in this case, square roots are pretty expensive compared to just simple comparisons. So with very little effort, we were able to really improve the performance. Again, you'll see a little bit of difference between the runtimes for the for the Intel and the AMD compilers. In this case, the AMD compilers were just a smidgen faster, and I think you're going to find that generally holds when you're running non-expense. But again, be sure to test the compilers to see which gives you the best performance. All right, so that's going to be the last example we're going to do today. I'm just going to run through a few more techniques, and then maybe cut you loose and see if you have any questions. So to me, this is where things get really interesting, where we start doing interprocedural optimizations, where we're looking at a high-level view of the entire program, spanning multiple functions, maybe multiple files. So a lot of what we did, optimizing loops, unrolling and fusion and splitting and peeling and so on, the compiler can do a lot of that. But the compiler can rarely recognize opportunities for interprocedural optimizations. Basically, looking at the code as a whole and figuring out where changes in one routine can be made that would affect another. And this really requires an intimate understanding of your code. And often these optimizations depend on recognizing operations that are repeated on the same set of the data from one invocation of a function to the next. So earlier, when we did that gprof example, we saw a good example of interprocedural optimization where we had some simple functions or subroutines that were all in one file, but we might have gotten lucky because all that code was in the same file and it was relatively simple. So I'm going to go back to a problem I mentioned earlier. This was in flow cytometry. This is a technique used to characterize cells based on molecules that they express on the surfaces. Immunologists use this technique a lot. It can be used for everything from basic research to diagnosing leukemia. Now, taking these cells, though, and sorting them into different populations is a really computationally challenging problem, especially because we're not looking at just one or two cell markers, but we might be looking at a handful. We're working in a, say in a 6 to 20 dimensional space. So I'm not going to get into the details of the code, but we noticed as we were working with code that there was a function that was called 5 times. So this is the get average dist function. 5 times with slightly different arguments. And I'm highlighting the differences in red, but all of the other arguments, temp sub I, temp sub j, population ID, numreal pop, file len, etc., these were the same for each of these 5 successive calls. So, and I know the next slides are going to be a little hard to find, but we found that that there were some calculations that did not depend on this first argument, that they just depended on the subsequent arguments that again were the same for all 5 calls. And we were able to pre-calculate some of these results. Therefore, pre-compute results, here we call them Pact 1, Pact 2, and Pact 3. And I know it's really hard to look at somebody else's code, but what we were able to do by pre-computing these, and of course you're going to use a little bit more memory, but you're going to get a big speed up. In this case, this one single optimization led to a 3x speed up of the program. So let me just flip back again. Yeah, so it's a little hard to follow, but basically using these pre-computed results, we were able to get that 3x speed up. And again, it's the kind of thing that you can only do if you really dive into the code and understand the semantics. Now, another technique that I like to use, and there's got to be a name for this. I've not been able to find it anywhere though, and I've used this successfully a few times, is that sometimes you can approximate an expensive function and redo the accurate calculation only when necessary. So let's say we have conditional tests, and it is very infrequently true, and that there exists an approximate test that is much faster than the exact test, and that we understand the error in that approximate test. So as a concrete example, this was a graph theory collaboration I was involved in, where a big chunk of the time was spent in this comparison. And you don't have to worry about what xprod and xi and xj are, but the key point is that we're comparing the arc costs of xprod to the absolute difference between xi and xj. And those arc cosine calculations are really, really expensive. There's kind of a hierarchy of expense, with addition and subtraction, multiplication being very cheap, followed by square roots and divisions, followed by exponentiation, logarithms, and trig functions. And at the very top, these inverse trig functions are very, very expensive. So what we were able to do, I jumped ahead here, is we were able to find a pretty good approximation to the arc cos function, this pi over 2 minus ax squared minus bx, with a known maximum error, and that was about 20 times faster than acos. So what we did was, first we did this this faster calculation. We did our approximation to the arc cosine, and we compared it to the absolute difference between xi and xj plus the maximum error. And then if we found that that condition was true, then we went back and we redid this expensive calculation. So it may seem like we're doing a lot of work, but in this case, we were able to really minimize the number of those expensive calculations. And in the case where the arc cost of xprod is truly less than the difference between xi and xj, we just add a little bit of extra work. And by doing this, we got close to a 20x speedup, since this condition is so rarely met. So with that, I'm just going to start wrapping things up. Have a little summary. Optimizing your code reduces time to solution. It can save energy. It can make your compute resources go further. Before you get started, optimize your code. Make sure it's worth your effort. How heavily is the code used? Is it going to help you get your science done quicker? If it's a code that runs in the blink of an eye, say 10 seconds, and you just need to run it every now and then, don't bother optimizing. But if it's something where it's taking hours or days or months to run, yeah, then you probably want to optimize the code. Optimizations can sometimes change your results. Remember that floating point identities are not the same as algebraic math identities. Ask yourself, how critical is the reproducibility? In most cases, you do not need bitwise reproducibility. When you're profiling your code, profile, optimize, repeat, because you're going to have new hotspots. Take advantage of those optimized libraries and the work of others. There's a mantra in software development. They say that good programmers write good code, great programmers steal great code. So if somebody else has written something for you already, if there's a library for Fourier transforms or eigenvalue solvers or linear algebra, go ahead and use that. We talked a little bit about what the compiler can and cannot do. Know the capabilities and limitations of the compiler, but don't rely on the compiler to fix all of your bad programming practices. Optimizing for cache is critical. Exploit that spatial and temporal locality. This is going to be especially important when you're working with multi-dimensional arrays. And then finally, sometimes the biggest payoffs come from that deep understanding of the semantics of your code. Knowing the structure of the data, knowing that, say, arrays are monotonically increasing, having that big picture across multiple routines. So with that, I think I'm going to wrap up. It is 2:21. If you are really interested, there is a bunch of slides in here in using the AMD uprof tool. I'm going to guess by this time everybody's brain is pretty full, so I'm going to leave that to you as homework. And with that, I'm going to stop sharing and see if we have any questions or comments. So if there are no questions, I am going to go ahead and wrap things up. I know this was a lot of material. Thanks so much to those of you who stuck around. And any questions, feel free to ping me in the Slack.